we said that if we repeat splitting the data, if each one of you sets a different seed on your R program and selects 1/3 of the data, you're all going to have different data sets. Okay? And if your data is smaller, there's going to be more sensitivity, right, to what your error rates are going to be. If we do that 100 times, we kind of figure out that, what that bias, we try to estimate essentially the bias. When we're collecting all these 1/3 samples, there's some bias in there depending on what we select. And we're kind of trying to average out. And we saw these nice curves. One was red and one was blue, the training and the test, and all of the different realizations over that. And although they were quite different, those bands were quite big, if we're using that for model selection, it doesn't matter. Because usually when I do cross-validation or I do the holdout method, I'm using it for selection. I'm not actually saying that's really what the test error is going to be. I'm just trying to find the best model. I mean, we have an estimate of the test error, but we don't really put a ton of faith into that estimate because, of course, we have smaller data sets. These are population studies. Okay, so you need really massive cohorts to say anything usable there. Cross-validation is one of the most widely used methods. And we talked about what it looks like. Leave one out cross-validation is a special case of, okay, important point. Leave one out cross-validation, what is it? It's a special case of k-fold cross-validation. It's very useful when you have small data sets, okay, limited number of observations, and you're simply leaving one out at a time. So it's k-fold cross-validation where k is equal to n, okay? Now, this is very useful. People don't always like it because if you think about it, the training sets are very, very similar, right? So people think that it tends to overfit. But in practice, it can work quite well, especially when your hands are tied and you don't really have any other way to select your models. You can usually use, in small data sets, people use AIC or k-fold cross-validation. Leave one out cross-validation. Okay, so those are kind of the two options. Or a bootstrap. So that is a special case of this, where here we're randomly selecting these different numbers. This is the picture in your book. They represent indices of individuals, and they're randomly selected and put into folds and so forth. Okay? All right. So this is all, we did this all last time. We talked about K, how to choose K. This was a nice figure that kind of demonstrated that here's the size of the training set, and this is the accuracy, okay, 1 minus the error. You can kind of see that as you approach larger data, the accuracy kind of gets asymptotic to 0.8, okay? So that's good. But actually cutting down the differences between, if this was 5-fold cross-validation, right here, we'd have a data set of about, if we had 200 in our training set, this would be the size of the training set. If we use the 5-fold cross-validation, doesn't change very much from if it was 80, okay? There's not much difference. But as we come over here, we see there's quite a difference. When the training set is too small, cross-validation tends to underestimate the accuracy or overestimate the error. And remember, we said that that's kind of conservative. We're okay with that, right? It's better than what we saw in this paper. What we'll see today is overselling the model, okay? Getting estimates that make the model look too good, okay? We're kind of conservative. We want to be conservative. That's very important. So this is a nice demonstration of that. That's just on simulation, and that doesn't always happen. It's not a golden rule to say that cross-validation always acts like that. But by and large, it often does, and that's why people kind of go to it over some of the other methods that we talk about. Okay. Selection of K is not very easy to make. Usually we try a few different Ks, and we look at the error bars. We try to see like kind of what curves look good, how we can get good estimates. But this particular example here, this is tenfold cross-validation. This is for subset selection, so we have subsets of different sizes. Okay, this of course is this would be, I think this is the Bayes error. I'm not sure, but this here is obviously a cross-validation estimate. Okay, and the true subset. So this is like in your homework, you're going to have to do a simulation. You're going to have to pretend that some of the betas are 0. Okay, so you're actually using a data set that has uninformative variables in it. That would be something like this. So if there are 10 important variables, this is the true answer. This one gets it right. Okay, it does. It gets it right. If you're to go by a minimum, we have something like this. We would take this. But like everything, we want to take a holistic approach to what we're doing. So we want to kind of look at the profile, and what we see is that although this is clearly the min or the best model, let's look backwards. If I look backwards, I see that 9 is almost no better. In fact, the standard errors are completely overlapping. So could you really say that one is better than the other? Okay, it would be hard to say that. It turns out we can use something called a McNamara test statistic to kind of figure out if one is better. It's not a great way to do it as a categorical test, but let's just think about the profiles themselves. All things being equal, we're looking at a profile. What are you going to tell me? That this is really better than that just because the mean is a tick lower? Even if it was truly better, I might rather run away with 9 variables than 10 because we're always going on the side of parsimony. But what people suggest is you use something called the one standard error rule. Okay? And the one standard error rule says that you take the most parsimonious model such that there is no more than one standard error above the best model. So it's kind of a funny way of wording it, but here I've got this one here, and I essentially look back. Is this one standard error worse than this one? No, it's not. So now I'm going to go here, and I'm going to look back. Is this model one standard error worse than this one? It is. So I take it. Okay, so now I can actually take this model because I know if I go back, then I really lose something. Okay, and if things are within one standard error of each other, we say, well, they're pretty much the same, right? So I don't have a clear picture of if it is better or worse. So that's the idea of the one standard error rule. You find the minimum and you look backwards. And you make sure that that minimum is one standard error one standard error better than the next best model. Okay, so that's the idea. Now, that's all well and good if you have a nice curve. Okay? What in practice and what you'll see is that we don't always get this nice U shape. We might have a bunch of weird things happening, especially with methods like KNN. And it's not so easy. And here's the other thing. You might not have one standard error anywhere. Okay? The models might be very, very close. Then you have to kind of use your judgment. Okay? In the LASSO lab, we also used tenfold cross-validation in there. You could see a profile with error bars. They're quite big usually. You're never going to find one standard error there. Okay, so in practice, this is really nice in principle, but not in practice. It's something we hope for. Okay, now, this is going to lead us into eventually this paper. And so, what is the wrong way to do cross-validation? Consider the following experiment. A massive number of predictors and a small sample size. For example, n is equal to 50, p is equal to 1,000, and there's a two-class output that is independent of the predictors. Okay, this is a really important thing. So we've got essentially an output that is independent of the predictors. So in this class, we play kind of two games. One is we try to get accurate predictions using test data, training data, and so forth. Another game we play, especially in the model selection chapter, is we try to figure out if there's no information in the data set, what are we going to learn? Ideally, we'd like to learn that there's also no information in the data set. But sometimes we learn that there's signal there when there's not. That's what we don't want to happen. That would be the opposite of conservative, right? So that's what this is trying to get at. So the wrong approach, so this is the data set. Now, ideally, you're given this data set, you don't know there's no signal in it, okay? There's no information in the data. You don't know that. And you have to go through the process of analyzing the data. So this is the wrong approach. Number one, so first of all, it's high dimensional. Screen the predictors. Find a subset of good predictors that show fairly strong univariate correlation with the class labels. Okay? So we're pre-screening the data. We're looking at, we've done this before, right? We've pre-screened the data. We looked at stuff. We tried to establish relationships. We may have dropped variables that were correlated with each other, right? Gleason, and there was some other thing one time that we cut out because they were correlated with each other within X. We've also looked at associations with Y, but we have not filtered with respect to that. Okay, so this is saying the wrong approach is to do the following. And unfortunately, this is a logical thing that somebody might do. Screen predictors, find a subset of good predictors that show fairly strong correlation with the class labels. 2, using this subset of predictors, build a multivariate classifier. 3, use cross-validation to estimate the unknown tuning parameters and to estimate the prediction error of the final model. Okay, this is a train wreck, although it looks completely fine. So this is a very important 2 slides that I'm showing right here, okay? Because unfortunately, although this is a train wreck, people don't realize it. And that is why, if you're very unfortunate, you don't realize it and you end up in PNAS where people are making fun of your problem with selection bias, okay? So it happens all the time in the literature. What is wrong with this approach? The first thing that is wrong, the predictors were chosen in step 1 on the basis of all the samples. Okay, so you took, and you can't blame somebody for thinking this way because you don't have that many samples to begin with. Okay, you only have a few. P is much greater than N, but you're doing a screening and you're doing filtering, and you are doing it with respect to the entire data set. Okay, so you're filtering, you're using the whole data, and you're using the response variable. So this is bad because you're cheating. Okay, you want to do variable selection, you need to do it appropriately. Okay, and if you already look at the response variable before you do any cross-validation or anything like that, you're kind of cheating. You're already throwing away things that you know are not informative. Okay. The second thing, you're dicing up the data after the fact. The test data has already been seen by the classifier. Okay? So you use a subset. First of all, you filter your predictors based on the response variable. So you see the answer. Then you use that set of predictors and you build a classifier. And then you divide into k-folds for cross-validation. Okay? So the problem here is that you want to essentially in order to not push through selection, what we call selection bias, you want to actually begin by dicing things up in terms of cross-validation and then going through a process of this type. Even so, we certainly would not want to, we'd have to be very, very careful if we're going to do any filtering. We don't want to bias our results by looking at the response variable, okay? In particular, in the test data should not be influenced by the training at all, okay? So these are some important features. Now, it turns out that these are very subtle points, and they're misused all the time, and we'll go through other examples. The true error rate is 50% because remember I told you that there's no signal in the data. So you got a 50-50 shot of getting a right classification by chance, okay, in that situation. So the true error is 50%. The predicted error rate is 3%. So it's a gross underestimation of the error. And that's generally what happens. It's very severe. Okay, this is the right way. So let's talk about the right and wrong way. The same exact problem. The first step is to divide the sample into k folds for cross-validation at random. Okay? Now for each fold, okay, one thing you could do, there's lots of ways to do this. One thing you could do if you need to do filtering, you could find a good subset of predictors that show fairly strong univariate properties or correlations using all samples except for those in fold K, the test fold. Okay? So what does that mean? Well, if I go back, way back when to this guy, okay? So I've got my test data. So let's just look at the first fold. I've got my test data and my training data which has been pooled. Now they're going to be big, okay? So the test data should be left alone. You should just leave it alone. This data here, if you need to do some kind of filtering, you can do that. You can do it in different ways. Generally, there's two things you want to do. One is that you don't want to look at Y, okay, when you do the filtering. So that means that common filters, for example, might be like look at the variance of each predictor or gene, whatever we talk about genes in here. So a high variance filter is a very common filter. In other words, if you do an experiment and you see some variables that don't change at all, chances are they're probably not going to be that useful, right? Because there's no change at all over whatever experiment you've just performed. So we can kind of get rid of them. So we call that a low variance filter. Okay, that's one way. Now notice that does not in any way look at Y. Okay? So low variance filter is okay. You could do, some people use a t-test. If you have a treatment in your experiment, you want to just do t-tests and look for significance. Again, that gets at the fact that are things changing in a significant way. But we're not using the response variable directly. Okay? So we can do kind of all of that. But what we don't want to do is we don't want to do anything until we divide into folds. Okay? I mean, we could do a low variance filter before dividing into folds. But if we're going to use Y, we need to be very careful that we only make decisions about what we're filtering based on that training set. The test set should not enter into play. The test set should be kind of locked up. Now eventually it's going to be unlocked and we're going to switch, right? But again, we want to be very careful. So generally what is done is that filtering step is done ahead of time, and it does not usually take Y into account. Okay? Now, so in other words, we've already divided into folds. We could do some things. I have here univariate, meaning going predictor by predictor. Okay, now, I mean, you could do some other things. I'm not saying lots of ways to do filtering. But univariate is not looking at Y. Using just this subset of predictors, build a classifier using all the samples except for those in fold K. This is just the application of K-fold cross-validation. Fit the model, right? Use the classifier to predict the class labels for the samples in fold K. So how does this differ? That's essentially the definition of cross-validation. Okay? Then you use it for prediction. How does this differ from here? Well, in many ways. It's valuable to go back and forth between these a couple times. Of course, here, the classifier is built before we even dice into cross-validation. So this is wrong in many ways. Okay? So it's one classifier, and then it's kind of that. The cross-validation is used essentially to get at the error rate and less to do with the model selection. Okay? So it's pretty bad. Okay, and in other words, cross-validation must be applied to the entire sequence of modeling steps. Samples must be left out before any filtering is done. That involves Y, I should say, also here. You could keep them in if you're going to do a low variance filter. Okay, that's what I say in this step. It is okay to filter on something that does not involve Y, for example, something unsupervised or involving variance. This is actually a major problem in the literature. Okay, lots of people make mistakes in this piece. And it's not just about cross-validation, it sneaks up in other methods too. Okay. So what are we going to do? We're going to talk about, this is kind of like the wrong way. This is like if you have your kind of a histogram or frequency of your sets of predictors. If you have a large P, you can kind of see this shift, right? So what you like is kind of this uniform distribution. Okay, you're not invoking any bias with respect to the response variable Y. But of course, the way, if you're invoking some selection pressure beforehand, your histogram is going to look like this with some kind of a shift here. Because you're looking for, you're pre-selecting variables that have good correlation with the response. Okay, that's not exactly what we want to do. Okay, now I've said, that's all I want to say about cross-validation. We're going to come back to that momentarily. Let me talk about the bootstrap real quick. We're going to denote the training set is Z, where Z is the pair xi and yi. Xi can be many x's, okay? The approach is very natural. It's a resampling technique. It's really easy to understand. I think that's why people like it so much. You essentially want to draw at random data sets with replacement from the training data. When you do this, each sample is the same size as the original training set. So you're taking bootstrap replicates. If your training set is 100, each bootstrap replicate will also be 100. You can do this B times. For example, big B is equal to 100. These we call bootstraps of data sets or bootstrap replicates more commonly. You refit the model to each one. Just like with the K-fold cross-validation, when you dice them up into fold and you fit the model, fit the model, fit the model. Here you resample the data, resample, fit, fit, fit. Okay, so that's the same idea. And there's lots of different bootstrap methods. We're talking about bootstrapping with replacement. It's a non-parametric approach. Okay, you can also do parametric bootstrapping and things like that. So the bootstrap is used everywhere. Okay, we're talking about it specifically with respect to model selection, but it's used in many, many different ways. This is what the picture in your text looks like. You've got your training data, Z, which is the XY pairs. X can be many features, it doesn't matter. These blue circles represent the bootstrap replicates. Bootstrap samples. Bootstrap data sets. So in other words, I'm going to randomly sample this with replacement, Z1, Z2 to Z big B. Okay, these are essentially data sets. Yep.
So it would be correct to say the difference between bootstrap and K-fold is in K-fold you divide the data set
Mhm.
to a certain number k, and
Mhm.
then will be change the test set around. And in Bootstrap, you can have a bigger sample size, but uh, this will be different data points. So, okay.
Exactly. Yeah. So no, the sample size will be the same. The sample size will be the same.
I mean, you can have a bigger sample size than k-fold
Mhm.
in a Bootstrap. For example, your training set can be bigger in Bootstrap, so that would make Bootstrap slightly better.
You'll see that there's pros and cons to both. So when you bootstrap, so if I were to bootstrap this class, what I would do is I would simply, let's see, there's roughly 20 of us here, okay? So I would simply take my jar with all the numbers in it, and I would pick out of my jar, but I would return the paper every time. So you might get selected 3 times, you might not be selected at all, you might be selected 5 times, but then I would have 20, and I'd write down everything, and then I would do it again, and I'd have another, then you might be selected twice, and you not at all, and so that's the idea.
Yes. But in a special case where your n is really small compared to b,
Mm-hmm.
doing k-fold leaves you with
Yes.
a smaller
Yes.
data set.
Yes, that is correct. Yeah. So when you're stuck in a jam when your n is small, usually Bootstrap is more advantageous in those scenarios, for sure. For sure. Yeah. Yeah. But Bootstrap, although it sounds like a great idea, right? I mean, there's a lot of things that are really nice about K-fold. Everything is used exactly once in the test set. Okay, so what you're going to see here is if I start doing this and refitting my models, there's lots of weird things happening, right? You're in the sample 3 times, you're not there at all, and the test set is a lot like the training. It's like you're refitting and applying the data multiple times. So we're going to come into some of those subtleties. What ends up happening is we have to make some adjustments to account for this fact that we're resampling with replacement. Okay? So, but once I'm finished pulling from the jar and I've got my bunch of Bootstrap samples, I can fit models to each one. Okay? Now this is representing, they call it a Bootstrap replicate. S represents any operation you could do on a data set. People bootstrap test statistics. Okay? We just finished a paper about Bootstrap clustering. Okay? So anything where there's uncertainty in the data and you kind of want to get some idea of confidence on your estimates, Bootstrap is used a lot. And there's lots of other fancy ways to bootstrap. It's very basic. There's Jackknife. There's parametric versions. Lots of things going on. We're going to see the bootstrap again, okay, in the context of random forests and boosting and bagging. But for now, we're just talking about selection, okay? All right, so this is any quantity computed from a bootstrap sample. Like I said, this is an example in practice where I've got 3 observations in an X and a Y column. This is the original data. These would be 3 bootstrap replicates, and what you can see, I just show this because it makes it more clear, like the question you asked. Sometimes somebody ends up in there twice, sometimes once, and sometimes not at all. So they look quite different, but every time a model is fit, okay? And sometimes we have to summarize over these different models. All right. So this is the training set as I defined it. The bootstrap samples, all defined as Z-stars. You can compute any quantity. For example, you can do a variance estimate, a mean estimate, t-statistic, clustering stuff, stability. So this is very useful. I'm going to kind of keep going here. But we're interested in error. Okay, so here's the obvious thing that you would do. You do this a whole bunch of times, and you would essentially do some prediction, and you try to figure out what the error rate is. Okay? So this is the most simple one. This is called error boot, and it's also referred to as error with a bar over it in your book. It's the same thing. Okay? So fit a model in question on a set of bootstrap samples and keep track of how well it predicts the original training set. Let f hat b star of xi be the predicted value of xi from the model fitted from the B bootstrap sample. Okay? So if I do that, essentially what I'm doing is I'm looking over, I'm taking the original training set. Here I got my models, fitting all my models. Okay? Fitting all my models. Here they are. I'm going to take the original training set and I'm going to push it through here and predict the response variable. And I'm going to see what the error rate is for this one. I'm going to see what it is for this one, and I'm going to see what it is with this one. So what do you think is wrong with that? Any ideas? What's one disadvantage of that? I'm going to use this guy. I'm going to push it back through here. One issue, important point, is that here I've got all my observations. I'm putting it over here. So here I've got 2 in here once. I've got 1 in here once. I don't have a 3. So 3 kind of feels like a test point, right? Because it wasn't used in the model fitting. 1 and 2 are kind of like training points because they were used in the model fitting. So I've got this kind of blend of test and training, and I'm kind of evaluating that. So it's kind of a training error, but it's kind of not. You see? Okay? So this is one of the criticisms of the simple error. Okay? You're probably already thinking, what could I do to overcome that? So this is the same. This is formal. We have the tailing of the loss function, whatever it is, because actually you can bootstrap regression or classification methods. You can bootstrap out any loss function. It's just tallying up over all the elements of your training set, which may or may not be represented in each B, probably not, probably in some, many times. It's random, okay? So I'm averaging over that, over all of the observations in each of the bootstrap samples. Tricky. The bootstrap data sets are acting as training data. The training data is acting as test data. They have observations in common. There's overlap. Okay? It's weird, and sometimes it overlaps bigger, right? Because you have more than one represented. So it's difficult to untangle, but you certainly can't consider it as test error because there's training points in there. Okay? It's a mixture. Okay. So what would you do? You know, if I really put the pressure on you and we had an ultimate time and I let you guys talk about it, probably you'd come up with something similar to cross-validation. Okay? In other words, let's look at this. Let's take a look at this data. And okay, let's write this down. I've got 1 in here. I've got 2 in here. I don't have 3. So let's see how 3 does. And let's write that down. That kind of could be like a test error, right? Likewise through all of that. So that's the second type of error rate, very similar to a leave one out approach, where if the bootstrap point is not included within that sample, then we kind of calculate the loss. This is an ugly equation. It's easier to verbalize than it is to write down, but you're essentially taking out the set of indices that does not contain I, and we can think about that. Okay? So this, they say, is not as sensitive to overfitting, of course, because we're kind of untangling that piece, but it is biased. There's some bias there. And now things get a little bit weird. So we saw both ends of the spectrum, okay? The problem is kind of the error bar, which was the original one, which tangled everything together, is kind of too good to be true, okay? This one, the one where you're leaving things out, it turns out, although they don't show it in here, it turns out that that's kind of, there's like an upward bias in terms of error. So it's kind of like too bad, okay? So the true error is somewhere in between. And so what some of the estimators that have been developed with respect to determining error rates in the bootstrap samples center on this idea of this is too good, this is too bad. And so we're trying to kind of find some balance between. So we have this weighting going on. And so the intuitive meaning here, so first of all, I'll show this kind of in a minute here. These coefficients are complicated to think about, but it essentially relates to the rates by which something can be picked up in a training or a test set. So here's, if you were to resample the data, it turns out that 0.632 is the proportion or the number of times that each individual would end up in a bootstrap sample. So it pulls things, it moves things around. It's kind of like, there's two examples that we kind of thought about already. One was QDA and LDA. Remember we were kind of pulling our covariance estimate toward the pooled one? That was kind of one example of this weighting idea. Another one is just recently, last time we talked about AIC and BIC, we talked about making an adjustment, okay? So it's the same kind of thing, it's an adjustment. So here, if we think about it, so the 0.632, probability of an observation in a bootstrap sample. So in this case, you kind of get, you've got all this 1 minus stuff. You've got 1 over, if everything is equally likely to get picked up, you've got 1 over n chances of being in the bootstrap sample. So here this is not being in the bootstrap sample n times, okay, because they're independent. And here we have 1 minus this quantity, and it's written this way for a reason, because the limiting function here, if I take this to infinity, is e to the minus 1, which is 0.632. This is just to say that this wasn't just pulled out of a hat, okay? So there's a reason for that. Now, the 0.632 estimate is okay. And so now you also read about that in this paper, different terminology though. A little different notation, but anyways, it's okay, it works well. But it can break down in overfitting situations. And so recently, I'd say more recently, they came up with another estimate. So here's an example they give. Again, 2 equal-sized classes with targets that are independent of the class labels. That's the second time I show you this one. When I say targets independent of the class labels, that means there's no signal in the data. Okay, so the error rate should be 0.5. Equally likely to get the answer right, guessing on true or false, right? So error 1 here is 0.5, but the 0.632 is 0.316. It's kind of an underestimate. So this one actually gets it better. It's pretty close in this case. It is the answer. Here, I've got an underestimate of the error. I don't want to have an underestimate of the error, okay? I don't mind overestimating it, but underestimating it is it could be very misleading. But I'll talk about that at the end, too. Okay, so what do? So this is when you have, this is in a situation of overfitting. So in other words, when all things are good and you've got a p that is less than n, you can usually get away with the 0.632 estimate. Okay, you can also probably get away with the leave one out idea. Okay, it's not unheard of. But when you have a lot of variables, this tends to overfit. So then they came across an idea to kind of try to estimate. Again, it's totally, it's not heuristic, but it's a lot of estimation. There's a lot of faith going on here. So if you know you're overfitting, they probably got together and said, how can we do this now? Well, let's estimate how much we're overfitting by and adjust it, right? So, I mean, of course, we're relying on data, so it's not a perfect process, but it's a smart idea. So just like they're penalty happy with respect to some of these estimators. So if we can estimate what we call the no information rate, and we have our value, we can kind of get an idea for how much we're overfitting. So that was the idea. The remedy was to take into account the amount of overfitting. So we let this gamma be the no information rate. That's the error rate if the inputs and labels were independent, just like I talked about before. So here I write gamma can be estimated by evaluating the prediction rule on all possible combinations of yi and xi. So this is one way, or you just think about it like this. If I've got my data and I've got my response variable and I just start randomly permuting it, right? If I just start randomly permuting it, I'm breaking the signal. And if I do that a lot of times and average it, here they say all possible combinations, but it's essentially a permutation, okay? Permute it a bunch of times, test it, and whatever error rate you kind of get is the error rate you would expect if you had no information in the data set. Because, of course, in the silly examples that I showed you, when I said, okay, well, the x is independent of y. In that case, it was a simulation. It was taken from a textbook. Each class is represented half, right? So I could say that, but you've got other situations where you've got weird things happening in the predictors, and you've got maybe classes represented in different proportions. So in practice, you can empirically figure out what that no information rate is by simply shaking up the data, just like you would shake up a snow globe, repeating the process of doing the classification or regression, figuring out what the no information rate is. Okay, so that would be the estimation of gamma. Now, here, R hat defines the estimated relative overfitting. It's always sitting between 0 and 1. I like to think of it, if you multiply this through by negative, it's easier to think about, okay? Because I think of it as an adjustment to the error. So here, if you multiply it through, then this is, of course, positive, and this is the subtracted piece, okay? So if the no information rate in that case is very big or close to the training error, then this is going to be very high. It's going to be closer to 1, okay? So this is just a ratio. It's something that they want to use in connection with this 0.632 estimate. So now they call it the 0.632 plus estimate. I don't know how they come up with these terms. The plus is supposed to, indicate, I don't know, I'm thinking about car models and stuff. To me, it's kind of misleading because it sounds like it's always better, right? But it's actually just taking into account this relative overfitting piece estimated by the no information rate, which you'd have to do in practice using the data. So it's all data dependent. And then this is now a function of what we call W hat, which involves this relative overfitting ratio. So presumably, this is supposed to work better in situations where you might overfit. That could be especially when P is greater than N. Okay? So let me just tie this up here. The AIC, cross-validation, and bootstrap, they yield models that are close to the best. For techniques, estimating the effective, okay, this is something I used to talk about. I'm sorry, it's still in here. With the AIC and BIC, you have to kind of understand how many degrees of freedom are in the model, which usually isn't a problem, but sometimes it can be. Resampling in general is thought to do a better job in terms of estimating test error. Okay. Now, I guess I don't have, that's weird, I used to have a slide that compared the different methods. Apparently it didn't make the cut this year. But there is a nice picture toward the end of your chapter which looks at kind of the, I think it's called the percent increase over the true model in terms of error rates. And for that particular example, you can see that they're all pretty comparable. They weave an example all the way through the chapter, Okay, and it turns out that everything is pretty comparable. The bootstrap and cross-validation are usually, cross-validation is usually kind of the best method, in my own opinion, if you can afford to do it. Okay, bootstrapping is probably, in my opinion, the second best. Okay, I rarely use the AIC and BIC, but like I said, the data will dictate what you can do. And in the end, what you want is to be able to use whatever method you're working with to select a model. And oftentimes, any one of those will do the trick. Okay? And usually they will, maybe they won't agree, but they'll be in the ballpark. Okay? All right, so we're going to do a lab eventually with the bootstrap. It's a nice lab too. Okay. So let's see. It's 2:53. All right. All right. So I'm just going to talk about this for 10 minutes, maybe even less. Okay. All right. Well, you know what I think I'm going to do is I will put up a video for this particular thing, because I do, for those of you who came in late, I have to give a presentation at Roswell Park in about 15 minutes. So, yeah, that was a surprise, actually. So I want to talk about this paper, but I mentioned we're going to have a quiz on Tuesday, so I kind of want to just tell you in advance what some of the important pieces are. I have a really nice video that goes through this paper. It's about 30 minutes long, okay? This is one of my favorite papers, so first I'll proceed with that. First of all, it's in PNAS, which is a great journal, okay? And it exposes something that has bothered me for years and years and years, okay? And it bothers a lot of statisticians. So selection bias is alive and well even now. They talk about 3 different studies in this paper in which the performance was very much inflated as a result of the way that the errors were estimated. And what I like about this paper is they look at some of the methods that we've talked about: tenfold cross-validation, sample splitting, the 0.632 plus, which we just talked about. Okay, and they look at all of them, and you can really have a good impression of what is going on and why each scenario is particularly problem. So when I talk about this in the video, you're going to see I'm going to start with this again to reframe the problem of cross-validation. I'll talk about microarrays, not super important. There's 3 examples. So this is what you don't want to happen. You don't want to participate in a study, write a paper. You're all graduate students. But you don't want your references to be of this type, right? Where they're talking about the way you analyze the data and how misleading it is. Okay? So this happens, and these poor souls, their studies were essentially trashed because of the way they did this cross-validation. Now, unfortunately, this really gave bioinformatics kind of a bad name back in the day, and eventually all journals started to require some kind of validation study. Okay? So this, I go through, in the highlights here, I go through the different things here. Essentially, there's methods that do and do not correct for selection bias. They intentionally derive this cross-validation, 1LE, leave one out, internal error. It does not correct for selection bias. That's the important thing. Okay? So there's one that does not correct for selection bias, the rest that do. And they essentially go through and they talk about these different. What I want you to focus on is looking at these plots and trying to understand, what the important things are. This is colon, this is leukemia, and I'll go through the plots very slowly. Essentially, you can first of all see that the error rates are quite different, but there's a training error, and then there's this bias cross-validation scheme, which is very, very close to the training error, okay, where the other ones are way up here. Okay? So it makes things look exceptionally good. And here is another one for forward selection. This one was for support vector machines. You don't really have to understand the classifier to understand the concept of what was happening. But this one is perhaps my favorite picture. Okay, so this one you should really understand in the paper. In this particular one, they do very similar thing to what I talked about in terms of generating the no information rate, where they kind of generate these data sets that have no signal. So you could expect something around 0.5 in terms of an error rate. And the selection bias puts it at almost 0. Okay? So that's kind of an important point from here. So, with that being said, what I will do is I will post the video